Yes. Skip distance. Yesterday we stopped at skip distance. So we can resume our discussion from skip distance. Okay, I'm getting the replies. Okay, so I think we completed skip distance, including the derivation. So we will move on to the next topic, that is the lowest usable frequency. Okay, what can be the lowest usable frequency? I will start with the slide presentation then. Okay. Distance we completed. Now we will move on to the lowest usable frequency. So the lowest usable frequency, or LUF. We already know what is the maximum usable frequency and what is the critical frequency. That thing we already know. Okay. The absorption of a high frequency radio wave in the D region of the ionosphere is proportional to the inverse of square of frequency. Okay. As you all know, the ionosphere is absorbing some frequencies. Okay. So that is more prominent in lower frequencies. That means if we are using a high frequency radio wave. Okay, high frequency, why I am calling that high frequency as a low frequency here? Because normally we are performing our ionospheric communication in high frequency range, very high frequency range, and ultra high frequency range. Okay, so here the term high frequency means the frequency range. It does not imply that it is a high frequency we are using in the ionospheric propagation. Okay, it just implies that the frequency range. We are classifying frequency range into low frequency wave, medium frequency wave, high frequency wave, very high frequency wave, ultra high frequency wave, like that. Okay, so we are using high frequency wave, very high frequency, and ultra high frequency waves in the ionospheric communication. So in that, the lower frequency will be high frequency wave. In that sense, we are using the term high frequency wave. Okay. So yes, I am getting so many notifications in between. Okay. So all of you try to join at least on the correct time. Okay. Otherwise, I cannot conduct classes smoothly. So many notifications I keep on getting. Okay, at least you join 5 minutes before the class, then we can complete all these formalities before the beginning of the class. Okay. So I think now we can see the slideshow. Is it visible? The slideshow is visible to everyone? Yes. Okay, it is visible. Okay, then yeah. I was telling about the lowest usable frequency. Okay. So the D region, it is absorbing the frequencies. So it will absorb high frequencies. That means high frequency range. Frequencies coming in high frequency range will be more absorbed by the ionosphere or D region of the ionosphere. So there is a frequency limit below which the signal to noise ratio fails to reach an acceptable value. That means there is a frequency limit below which the absorption will be more. The absorption is more means what? The signal to noise ratio fails. That means the signal is getting absorbed and noise is added naturally. So there is a lower limit for the frequency. That is called as the lowest usable frequency. And it depends on the transmitted power. Okay. Since our reception is mainly depends on the signal to noise ratio or SNR. Okay. If we are transmitting the signal with high power, then even though there is an absorption, or even though there is considerable amount of absorption, we will get some result at the receiving end. Okay. So, but what is the problem? We cannot increase the power beyond a limit. So, we should compromise in the frequency. We should not use very low frequencies. Okay. So, in addition to these absorption limitations, the signal loss occurs due to free space propagation loss, polarization change caused by a magnetic field. All these things we have seen already. Then scatter process. Scattering, you know what is scattering. Okay. What is scattering? The signal can get scattered due to obstructions, or while transmitting, it can get scattered. Okay. So, for a given distance of transmission and limited transmission power, the lowest usable frequency for skywave propagation is limited mainly due to two phenomena. Okay, already we have discussed these two. Already we have discussed. What are those two? First one is the absorption, and second one is the increase of noise with decreasing frequency. That we have discussed in the first class. Increase of noise with decreasing frequency. Okay. So that means in lower frequencies, the noise will be higher. And just now we saw what is the decreasing frequency with respect to increasing atmospheric absorption or ionospheric absorption. The D region will absorb lower frequencies within the within the radio waves. Okay, the lower frequencies will be getting absorbed. So we have to increase the power, but we cannot increase the power beyond a particular limit. Okay, and keep on getting notifications always. Okay, okay. So these both these things are limiting the lowest usable frequency. So we should not lower the frequency beyond a particular limit. Okay. So that's it. So we already seen what is the maximum usable frequency. Okay. The maximum usable frequency limits the highest permissible frequency for skywave propagation in a given path. Okay. Likewise, the lowest usable frequency gives the lowest permissible frequency. The maximum usable frequency was limited by the structure of ionosphere, or the maximum frequency of the wave which we can send without escaping it into the free space. Okay, that was the maximum usable frequency. Now we will move on to the lowest usable frequency. The lowest usable frequency is limited by the absorption in the D layer. Okay. So what will happen to this D layer during night? What will happen to this D layer during night? Okay, nobody is answering. Okay. Okay. The D layer will appear. Yes. One or two are replying at least. Yes. The D layer will disappear during night. Okay. So what will happen to the lowest usable frequency? The lowest usable frequency is mainly depends on two things. Okay, first one is absorption in D layer, and second one is increased signal to noise ratio. Okay, or increased noise level in the low frequencies. So during night, what can happen? The D layer is disappearing. There is no D layer at all. Okay, so the only thing which limits the lowest usable frequency is the noise. Okay, so during night hours, the lowest usable frequency, that is primarily limited by increased noise. The value of lowest usable frequency is calculated from the measurement of noise level at the receiving end and the estimated value of skywave absorption in the given propagation path. Okay, these two things are applicable for lowest usable frequency during daytime, but during nighttime, only the signal to noise ratio or the noise at that particular frequency is determining the lowest usable frequency. So how can we calculate the lowest usable frequency? How can we calculate it practically? Just start sending a signal at a lower frequency. Okay, at a lower frequency, send a signal from a transmitter to receiver through the atmosphere and measure the signal to noise ratio at the receiving end. Measure the signal to noise ratio at the receiving end. And just monitor or just check whether the signal to noise ratio is coming under acceptable levels or not. If the signal to noise ratio is coming under the acceptable levels, then it's okay. The point where it started to fall below the acceptable level, that particular level is the lowest usable frequency. Okay. I think you might have understood this. So this is in this figure just shows the increase in height of flare during night and hence the need of day and night frequency. Okay, so we already told that during day and night, this lowest usable frequency is determined by different things. Okay, during daytime, D layer is present, so D layer absorption plus the signal to noise ratio or the noise in that particular frequency both affects the lowest usable frequency. Okay, but during night, as you can see in this diagram, the D layer is disappearing. So that means the same wave has to reach to much higher levels in order to bend down to the receiver side. Okay, so for that particular time or for during night time, the lowest usable frequency will be a different one. Okay, so that is, you can understand, that is quite natural thing. Okay, so what will happen to skip distance? That is clearly shown in this figure. Okay, during daytime, D-layer is present, so the wave won't transmit much higher. It will get reflected from D-layer itself, so skip distance will be small. But during night time, for the same wave, it has to transmit up to E or F layer because this D layer is not at all present. So it will reach up to E layer and it will come back. So consequently, the skip distance will be more. So to maintain same skip distance, it is better to use two different frequencies during daytime and night time. Okay. So normally we are using two different frequencies for day communication and night communication. Okay. So now we are moving on to the next topic. Okay. So we have already seen the types of propagation. Okay. In that the characteristics of skywave propagation, we all seen what is critical frequency, what is maximum usable frequency, what is this lowest usable frequency. All these things we have seen. Okay. Then one more thing we need to see. Yes, one more thing is there. optimum working frequency. I think yesterday I told this. Okay, anyway, we will just one more time. We will just review these things. Yeah. Yesterday I discussed this thing. Okay, whatever. We'll move on to optimum working frequency. Optimum working frequency. What is optimum working frequency? Optimum frequencies are selected from the prediction of maximum usable frequency based on monthly average. That means yesterday I told already this maximum usable frequency, it differs from time to time. Okay, it is highly dependent on the changing characteristics of the atmosphere. So we cannot strictly say that if we are having a maximum usable frequency, we can use that in all time. We cannot say that because it is highly depending on the structural changes in the ionosphere. So we have to select an optimum working frequency which we can use for our communication. Okay, so we will take the predicted values of maximum usable frequencies on monthly basis, and we will take average of that. So if we are having an average value of that, from that we can arrive at a particular frequency that is called optimum working frequency, which can be used effectively for our communication. Okay. So normally this optimum working frequency, we are fixing it between 50 to 85% of maximum usable frequency. Yesterday, you might be remembering, I told we cannot use 100% of maximum usable frequency. Okay, we will use it at 80 to 90% of maximum usable frequency. That's why here we have taken that 85%, 80 to 90%. We are taking middle of that 85%. So for optimum working, we can select a frequency which is in between 50% to 80% of the maximum usable frequency. Okay. And of course, this varies from season to season and day to night. Why? It varies from season to season and day to night. Why? Because the structure of ionosphere or ionospheric properties varies from season to season and day to night. So for continuous communication, as we have seen already, the lowest usable frequency will change from day to night, and this optimum working frequency, maximum usable frequency, everything will change with respect to season and with respect to day and night. Since the structure of ionosphere or ionospheric properties are changing with respect to season and with respect to day and night. So we have to use separate frequencies for day transmission and night transmission in order to have uninterrupted transmission. Okay. So typical frequencies for day and night, we are using a 6450 megahertz and 5000 megahertz. So during night time, we can use a smaller frequency. Okay, because during night ionospheric, that ionic density will be lesser. So we can use a lower frequency for getting the same transmission. Okay. So we have seen optimum working frequency, maximum usable frequency, lowest usable frequency, critical frequency, everything. Okay. Now we move on to our next topic, that is normal and abnormal variations in ionosphere. Okay. Normal and abnormal variations in ionosphere. So while discussing all these topics, I have told you the ionosphere is not constant. Okay, the ionosphere is always keep on changing. The ionosphere is not at all constant. Its characteristics, its properties are keep on changing. So, we can call it as abnormalities. We expect the ionosphere to be normal, but it is not the case always. Some abnormalities will be there. That abnormalities we are going to see, and we are going to see how it is going to affect our communication. Okay. So it is mainly classified into two: normal variations and abnormal variations. So normal variations means that we expect it as normal, or we can consider it as normal. Those are the variations: periodic variations, seasonal variations, height and thickness variations. That means periodic variations means what? Day and night variations that we can expect. Like we are expecting that it is normal, it is absolutely normal if the delay is vanishing during night, because that is the characteristics of that delay. Okay, so seasonal variations during the summer season, we expect the thickness of ionosphere to be more, or it is the ionosphere is more ionized because more sunlight is incidenting on summer season, so we can expect that. And height and thickness variations. Height and thickness will vary according to the sunlight and according to the exposure of sunlight, for how long that particular region is exposed to sunlight. All those things that are normal only, that we can understand. So those variations are normal variations. That means conditions in the ionosphere vary throughout the day with angle of sun's rays, and in addition, they vary quite regularly with the season of the year. Okay, so those variations we are calling as normal variations. Then second one, abnormal variations. Okay, abnormal variations means they are unexpected. So all these variations are occurring due to sun only, mainly due to sun. Okay, so in abnormal variations, it includes sudden ionospheric disturbances, ionospheric storms, sporadic E-layer reflections, tides and winds, sunspot cycle, fadings, whistlers, etc. etc. I think almost 11 abnormal variations are there. So we have to see one by one. Okay. So I think you might be remembering what is a sporadic E-layer. Here we are saying about sporadic E-layer reflections. What is a sporadic E-layer? Anyone remembering about sporadic E-layer? Okay. If anybody is remembering, just type what is sporadic E-layer. In the meantime, I'll take your attendance. Sporadic E-layer 90 kilometer to 130 kilometer. Okay, why it is called as sporadic, or what is the speciality of that? Yes, production of clouds, unpredictable. It is not fluctuated. Yes. Presence of clouds. Okay, yeah, I'm getting at least some answers. I'm happy. At least some of you are listening. Okay, so yeah. Okay, let it be there. I was just checking where you are remembering the things or not. We will move on to the abnormal variations. First, sudden ionospheric disturbances. Okay. Sudden ionospheric disturbances, or SID, or it is also called as Mongel-Dellinger effect. Okay. SID is caused due to sudden solar flares. What's a solar flare? This SID is means sudden ionospheric disturbance. That means a sudden disturbance is occurring in the ionosphere. And it is caused due to sudden solar flares. So we have to see what a solar flare is. Okay. A solar flare is a sudden flash of increased brightness in the sun, usually observed near the surface. We are considering our sun. Near the sun surface, a sudden flash of increased brightness can occur at some time. That is called a solar flare. Okay, I will just show you a video which shows what a solar flare is. Okay, it is the video is I found it in NASA's site. Okay, so is it visible? At least you will be seeing an image. Is it visible to all? No. Can you see the image at least? No. Okay, okay. Okay, I will share. I'll okay, you're seeing PPT only, and that's the problem. Okay, I will present it as a separate window. Can you see it now? Yes. Okay. So here, this picture shows what a solar flare is. You can see the brightest outputs from on left side and right side. Okay, that are solar flares. That means a sudden increase of brightness at some specific points. Okay, so there is a video also. I will just 40 seconds video. I'll just play and you can listen and you can understand what a solar flare is. See that they are showing how that sudden brightness is coming out of the sun. There is no audio for this video. Only video is there. Okay. So this is the normal surface of sun. From that surface, sudden increased brightness can come out like this. This is called solar flares. Okay. So these solar flares can reach up to the ionosphere. Okay. So I think now we can see the PPT. So these solar flares include X-ray radiations, alpha rays, like that. So if X-ray and alpha rays are present, what will happen? It will ionize tremendously the ionosphere, or the ionic density in the ionosphere is going to increase tremendously, and this effect is much intense that up to D layer it is getting affected. Okay, the solar flare means a flash of increased brightness. Okay, just like a storm of heat is coming, like that only it is going to enter into Earth's atmosphere. It cannot predict it, when it will happen or how it will happen, how intense it will be. It cannot be predicted. That's why it is included under abnormal variations. So due to these solar flares, the ionic density of the ionosphere is going to increase abruptly. Okay. So as a result of increased ionization density, absorption of short waves, that means high frequency waves, increases, and reflection of atmospheric noises also increases. Okay. So this is an abnormal variation, and it is first observed by the scientists Mongel and Dellinger. So it is also called as Monger-Dellinger effect. Okay. So This is called sudden ionospheric variations. Okay. So the value of lowest usable frequency increases beyond maximum usable frequency. The value of lowest usable frequency increases beyond maximum usable frequency, and it results in a complete blackout. Okay, we already seen that in the previous slide. We already seen that the ionic density of the ionosphere increases, and reflection of ionospheric noise also increases. The ionic density increases means what will be the natural consequence of that? Ionic density increases means the reflection will get increased. The refractive index will get minimized and the reflection will get increased. So the lowest usable frequency that increases beyond the maximum usable frequency. How that will happen? The absorption of the ionospheric layers is also increased. So the lowest usable frequency will increase and it will keep on increasing and it will keep on increasing, and at one particular point it will cross the maximum usable frequency. Similarly, the maximum usable frequency will keep on decreasing. Okay, so at one middle point, this lowest usable frequency will cross the maximum usable frequency. That means what? We cannot communicate at all. The lowest usable frequency is beyond the maximum usable frequency. So it is called as complete blackout. No ionospheric communication is possible under these circumstances. Okay. So the phenomenon of complete blackout is known as SID and was first observed by Mongan and Dellinger. Hence, SID is often referred to as Mongan-Dellinger effect. Okay. So these are just theory only. Okay. Next, we will move on to ionospheric storms. So, ionospheric storm. What is an ionospheric storm? It is a turbulence in the ionosphere of Earth's atmosphere. We know what a normal storm is. A normal storm എന്താണെന്ന് അറിയാമല്ലോ അല്ലേ? So, an ionospheric storm means a storm in the ionosphere. Normal storm is a turbulence in troposphere. But a turbulence in the ionosphere is called ionospheric storm. It is triggered by enhanced flux of energetic electrons that are emitted at a large level by the sun. Okay. Sometimes from sun, an enhanced flux of energetic electrons can happen. And if that is entering into the ionosphere, it can cause a turbulence, or it is referred as ionospheric storms. So it is not that much severe as the SID. Okay, we have already seen that SID will result in complete blackout. So this is not that much severe as SID. It will affect topmost layers only, like F2 and E layer. Okay, so there is a video regarding that, how an ionospheric storm is occurring. That I will just show you. Okay, is it visible? No. Is it visible? The video is visible? No. Okay, let me try once again. Okay, I think now it is visible. You can see. It is just okay, just a window only, and that you can see solar. Okay, you can see like a moving figure on the left hand side. I think you can. Yes, yes, yes. Okay. So this is an ionospheric storm that occurred during April 10 to 11 of 1997. Okay, during 1997, one ionospheric storm occurred. Okay, this is the graphical representation of that. Okay, this is a 24-hour long simulation. So in this, you can see there this yellow and red colors, they are showing increased ionic density. So that increased ionic density is flowing as a storm above the globe. Okay, you can see the globe, and above the globe, like a storm only, it is moving. It will circulate. Okay, the UT means universal time. You can see with respect to each hour how the storm is coming and going. Okay, it's the graphical representation of the atmospheric storm. It occurred during 10th April to 11th April. Okay. So this how this will going to affect our communication? How this is going to affect our communication? As you can see, this in the storm itself, it is having high variation of the ionic densities. So of course, the properties of the ionosphere is going to change beyond our control. So definitely, it is going to affect the critical frequency. Everything, it is going to affect everything. So this is one abnormal irregularity. Okay, so we will move on to the next irregularity. That is sunspot cycle. Okay, what is sunspot cycle? What are sunspots basically? Sunspots. Sunspots are nothing but spots in the face of sun, or spots in the sun. Spot means what spot? There are some black spots in the sun. Okay, these spots we are using to identify the sun. So, as you know, sun is rotating on its own axis. So, with the changes of these spots, we can identify how the sun is rotating. So, these sunspots are having a cycle. That is, once in every 11 years, it is going to repeat. So, what does that mean? Once in every 11 years, the pattern of sun's radiation is also going to repeat. Okay, the sun has an 11-year cycle over which its output varies tremendously. Okay, it has been observed that ionospheric characteristics closely follows the sunspot cycle. That is obvious because the ionosphere is always depends on the sun's radiation. So if the sun's radiation is going to change over a cycle, the corresponding change will happen in the ionosphere also. The critical frequencies of ionosphere are highest during sunspot maxima and lowest during sunspot minima. That is also quite understandable. During sunspot maxima, the sun activity, solar activity will be more, and the ionosphere will also vary accordingly. And during the sunspot minima, the solar activity will be minimum, so critical frequency will be minimum. Okay, so here also one video is there. So I will show you. That is from NASA's website only. That will give you an idea about what a sunspot cycle is. Okay. Is it visible? Yes. Okay. So you just listen to that video, and then you will get an idea of what a solar cycle is. Okay.
When we look up at the sun from Earth, it seems calm and unchanging. The truth is quite different. In addition to these abrupt changes in activity, the sun also has a long-term, more regular pattern of change. This pattern is called the sunspot cycle, and a single cycle lasts for about 11 years, although it can be as short as 8 or as long as 14, and it can vary dramatically in intensity. During one cycle, the number of sunspots, a good indicator of solar activity, goes from low to high and back down to low. Solar minimum represents a period of time when sunspot numbers are relatively low, and solar maximum represents a period when sunspot numbers are relatively high. During this cycle, the location of the sunspots also changes. They are at middle latitudes during solar maximum and move closer to the equator as the sun approaches solar minimum. At solar minimum, there are sometimes no sunspots to observe. At solar maximum, there can be many at the same time. The number of sunspots is important because sunspots are the visual markers of where powerful magnetic fields have emerged from the sun's interior. These magnetic fields power solar flares and coronal mass ejections, which can affect Earth and other objects in the solar system. As the sunspots increase, so does the frequency and severity of flares and CMEs. The sun's 11-year cycle is a symptom of a longer 22-year cycle called the solar cycle, or Hale cycle, which affects the sun's magnetic fields. Every 11 years, the sun's poles flip. North becomes south and south becomes north. So every 22 years, the poles return to the position where they started the cycle. The flip is due to the complex movement of magnetic fields inside the sun that are constantly stretching, twisting, and crossing as solar material bubbles up from the sun's core. But the exact pattern of movements is not yet mapped out. Because the sunspot cycle follows a similar pattern regardless of the orientation of the poles, it only takes half as long as the solar cycle. The two cycles are different, but the 11-year sunspot cycle is often referred to as the solar cycle, which can be a little confusing. Right now, the sun is approaching solar maximum, so flares and CMEs are more common than they were a few years ago. This cycle may peak in 2013 or early 2014 and should reach its minimum around 2020, although predictions about the sun are still uncertain. The slower than expected progress of this sunspot cycle has led some to speculate that the next sunspot cycle might be very minimal, with few sunspots even at solar maximum. It is still far too early to know, but even if this is the case, it has happened before and isn't something to worry about. It just means that the sun would briefly be a little closer to the unchanging orb it looks like from the ground.
Okay, so I hope you all might have understood what is a sunspot cycle and how it is going to affect the Earth. Okay, in that it was there clearly mentioning like during the sunspot maxima, the solar activities will be more, and during sunspot minima, the solar activities will be minimum. Okay, so can anybody say like what is current sunspot cycle? It is maxima or minima in 2020? Can anybody say? It was clearly showing in that yes, it is minimum. Okay, so now we can expect it to be on minimum. Yes. Okay. So at least you are listening to NASA's videos. So already we have seen 3 of that videos from NASA. All are very interesting. Okay. So we will come back to our topic. Next, we will move on to next. Abnormal variations. Okay. Already we have seen sudden ionospheric disturbance or SID, then ionospheric storms, then sunspot cycle. Next, we will move on to tides and winds. Okay. The atmosphere experiences tidal pull of sun and moon. Okay. This is quite a natural thing only. Our atmosphere is always under the influence of sun and moon. Okay. Tide, that is due to lunar activities or due to moon's attractions on seawater. Okay. So likewise, the atmosphere is also experiencing tidal pulse. So naturally, the effect of tide is experienced most by the F2 layer, since it is the outermost layer. That tidal pull of sun and moon will be maximum at the F2 layer. Okay, winds. Winds means motion of ionized particles. Winds with respect to ionosphere. Ionospheric winds means motion of ionized particles. So winds in ionosphere are mainly caused by tides, just as our natural tides. Okay, natural tides means tides in the sea are causing by lunar attraction. In the same sense, we can understand this also. There can be some tides and winds caused by attraction of or tidal pulls of sun and moon. Okay, so this can also classified as an abnormal variation since the pattern is not known. Okay, so next abnormal variation is fading. Fading, you might have already heard about fading, like in digital communication and all. You are studying this. What is fading? What is fading? What is fading? It is the fluctuation in the received signal strength at the receiver. Okay. So fluctuation means the received signal strength at the receiver will be fluctuating. It will, like, we cannot correctly identify the received signal from the signal strength, or from the coming signals we cannot correctly identify the received signal. It is keep on fluctuating. So it is caused by the variation in heights and densities of ionization in different layers of ionosphere. So as we already know, the ionosphere structure of ionosphere is not a regular one. So there are chances of having different heights and different ionization densities. So there are chances of fadings also. You might have heard about multipath fading and all in digital communication, I think. So there is no need to do much explanation on this fading. Okay, we will move on to the various types of fading. Okay, so various types of fadings are selective fading, interference fading, absorption fading, polarization fading, and skip fading. Okay, so as the name suggests, selective fading, that is the frequency selective fading. It is more dominant at high frequencies for which skywave propagation is used. There is not much to explain in that. Okay. Frequency selective fading occurs in some particular frequencies only. So in high frequency, it will occur. That reason we already told how it can occur. We already told the high frequencies are getting absorbed, okay, in the D layer. So that fading can occur due to that. Okay. The next is interference fading. What is interference? Interference you already studied in the digital communication and signal processing, like signals and systems, everywhere you might have studied. Okay. So how that interference is resulting in a fading here, that only we are going to discuss. Okay. Here it is produced by the interference between upper and lower rays of skywave. Okay. Like in that skip distance portion, I have shown you that, like with respect to the angle of incidence, the wave will travel in different heights. So there can be an upper ray and a lower ray. Okay. So likewise, that rays can reach at the receiver through different paths based on the angle of incidence. So waves reaching the receiver by different paths and even between the skywave and ground wave. Suppose we are having ground wave propagation and a skywave propagation. Skywave we are transmitting, and it is coming back to the receiver. The receiver is located in the ground. So definitely the ground wave will also be present there. So there are chances of getting these two waves interfered. So that also can result in fading. Okay, that is the interference between ground wave and sky wave. Then first one, interference between upper and lower rays of sky wave itself. Okay, when the same wave is traveling into different heights based on the angle of incidence or based on the particularity or peculiarity of the layers, based on the relative difference of refractive index of the layers or based on the angle of incidence, it can travel into different heights. So while coming back to the receiver, there are chances of getting these two waves interfered. Okay, since these waves both are traveling in different heights, there will be a phase difference that can contribute to a interference, right? That will result in fading. Okay. Next is absorption fading. This fading occurs due to variation of signal strength with different amount of absorption of waves absorbed by transmission medium. Okay, that explains itself. So this fading occurs due to variation of signal strength with different amount of absorption waves absorbed by the transmission medium. What is our transmission medium here? Ionosphere. Okay, here our transmission medium is ionosphere itself. So while we are transmitting through the ionosphere for different frequencies, different absorption can take place. Some frequencies will absorb, and some frequencies will get absorbed more, and some frequencies will get absorbed less. So based on that, absorption fading can also take place, absorbed by the ionosphere. These frequencies are getting absorbed by the ionosphere. So we have to increase the signal strength in order to get better reception. Okay. Next is polarization fading. This type of fading occurs due to the changes of polarization of the downcoming sky waves. Okay, as we already know, if a wave is reflecting, this polarization will change. Okay, like you might have studied in your optics classes. Yes, in 12th standard in optics classes, you might have studied circularly or the polarization will change if a ray is getting reflected from a mirror. The wave is getting reflected from a mirror, its polarization will change. Left will become right, right will become left. Similarly, here also, since the wave is getting reflected from the ionospheric layers, its polarization can change. So this will also result in a fading. Okay. So the downcoming skyway will be having a different polarization and it can also result in fading. The next one is skip fading. Okay. That is, any variation in the height or density of an ionized layer may move the receiving point in and out of skip zone. Okay, yesterday you might have seen, like you might have noticed what a skip zone is. Okay, if a particular wave is traveling to a larger height than expected, then skip zone will compress. Okay, and if the wave is not at all traveling to the height expected, then skip zone will increase. Okay, so this can happen due to the abnormal variations in the ionosphere. So what will be the result of that? Our receiver you might have placed in the exact position by calculating the skip distance and all, but due to these abnormal variations, the skip distance will vary. So we will not receive the signal as desired. Okay, so the receiving point will shift either towards in or towards out of the skip zone. Okay, so that will also result in a fading. So next we will move on to Whistler's, that is sixth abnormal variation, Whistler's, which is naturally occurring short-lived electromagnetic disturbances in the ionosphere. Okay, in the ionosphere, due to so many activities, due to so many natural causes itself, some electromagnetic disturbances can occur. So that is called as whistles. This is also an abnormal variation since we cannot predict at all how it is going to happen and when it is going to happen. Okay. Next one, seventh abnormal variation, Luxembourg effect or ionospheric cross modulation. This is basically ionospheric cross modulation only. It is first observed in Luxembourg. That's why it is called as Luxembourg effect. Okay. This interference occurs when two transmitting stations were nearly on the same circle varying from the receiver. Okay. Suppose there are two transmission stations within the vicinity of the receiver. There is a possibility of production of cross modulation products due to interaction of two strong radio waves passing through the ionosphere simultaneously. Suppose the two stations are located within the vicinity of the receiver. That means the two stations are transmitting, but the receiver will be tuned to receive one station only. But since the two stations are transmitting and the two stations are nearby, the power will be more. So these two signals can cross modulate. Now this can interact. So it will result finally in a cross modulation. Okay. So these two strong radio waves can interact together, and sometimes we will receive, if we are tuning for one station, we will receive the other, and if we are tuning for the next station, we will receive the first station. This thing can happen. Okay. So I think our time is up. So we can conclude here. It's 9:30. We can conclude.